Thanks so much. So first of all, I am just so excited about this event. I'm so excited to see everyone here, and I'm really honored to get to speak to such an incredible audience, ranging from statistics faculty to leaders of data science groups in industry. This is just a really wonderful coming together, and I hope I'll get to connect with many of you here or offline afterwards. So today, I want to talk about data-driven market design. And what I really want to do is inspire you to think about how bringing different disciplines and approaches together is crucial for solving a lot of the problems that are core to all the companies that make Silicon Valley exciting and vibrant. And so it's partly bringing disciplines together to solve important real-world problems, but also the fact that there's actually a ton of unsolved problems scientifically. And when you go out to solve real-world problems, the interesting scientific questions just smack you in the face. And so for both academics and for practitioners, this is just an incredibly exciting moment in time where collectively we're inventing new science and pushing out the frontier. So my experience with this really started with work I was doing on auctions, and I used to work in a sort of small data setting where I was trying to help design marketplaces, but old-fashioned marketplaces, like marketplaces for timber. And then in 2007, I started working with Bing Ads. Of course, it wasn't called Bing Ads at the time. It's been through a couple of names. But in that context, I was brought in to actually help them design their real-world online advertising marketplace. And that experience really was transformational for me. It put me as a lone economist in a group of hundreds of machine learning scientists and engineers, none of whom spoke my language. They kind of had an idea I was some kind of famous professor, but that got no credibility in terms of actually doing anything. And so if I wanted to accomplish anything, I needed to both figure out what the right answers were in a really hard set of circumstances that really hadn't been solved before, but then also learn to communicate in a very interdisciplinary environment. But what was really exciting was that there was so much to bring in from my perspective from economics and social science in managing a marketplace. And so especially for the students, I'd really encourage you to think about getting some types of sort of, domain knowledge, if you like, because one of the places that is really wide open and has a huge talent shortage is in the sort of business side of a lot of these tech firms, managing these advertising marketplaces from Twitter to Facebook to Bing to Google to now the new marketplaces, Uber and Airbnb and so on. When they first start, they have to build the systems, they have to get the machine learning right to kind of get the places going, but then once they start thinking about making money, it's an entirely different ballgame. So today I'm going to give sort of an overview of a bunch of the problems that I encountered and various sort of scientific inquiries that came out of that, but all sort of organized around the problems we were solving. I should mention one other thing, actually, since Jennifer Chase is here. One of the great things about collaborating with Microsoft in particular was that they had Microsoft Research, so I was able to work with the actual Bing Ads system, but at the same time do academic research for publication. And I think for those of you in industry, it's really a great idea, a great way to get sort of cutting-edge research into your companies to allow academics to come in and innovate and then publish their research. So just to get started, of course, what makes Silicon Valley hum are all of these marketplaces. So the new ones, Uber, Lyft, Airbnb, TaskRabbit, Rover.com, a dog walking service, Zeal. Did you guys know that you can push a button on your phone and a masseuse will come to your house in an hour with a table and give you a massage at 9:30 at night? Good if you've been sitting in front of your computer all day. All of these marketplaces are really much more complex from a data science and data analytics perspective than something simpler like just designing a website or even the algorithmic side of a search engine. Conceptually, those problems are much, much simpler than doing data science for marketplaces. And so I'm going to talk about all the complications that come up when trying to do data science for a marketplace. And one of the big aspects of it is that what a marketplace is doing is it's bringing together different groups of customers. And often the user side, the individual user side, is hard, but it's actually much easier than sort of the business side, the seller side, where you have people who are deciding, making a profit-maximizing decision of whether to come into your marketplace. They can be quite sophisticated. If you make a change, they're going to optimize against each other, against you. They're using computer programs to figure out how to maximize their profits on your system. And so their behavior can be much harder to measure and predict. So, when I think about marketplace design, just to get a sense of like what are the core problems that, that companies deal with and that economists study when it comes to marketplaces, well, you're bringing together buyers and sellers. And so what the platform itself has an enormous set of decisions to make, a really wide range of choices. They have to figure out, how do you price? What's the pricing model? Who sets the prices? Does the seller set them? Does the platform set them? How do I charge? Do I charge people for posting a listing on eBay? Do I charge a percentage of the transaction? Lots of different options there. And then the sort of the science in the background, I have all these algorithms. I have these algorithms that figure out when you put a query into eBay, when you put a query into Bing, which ads show, which algorithmic results show. When I put a query into eBay, which sellers do I put forward? And those algorithms are really at the heart of innovation for these companies. And if you want to think about how would I make 10% more money at eBay or 10% more money from my advertising or so on, that's generally going to come through innovations in the algorithms. And so you're going to have one set of rules, one set of machine learning algorithms that are used to decide what to put forward. If you have a new innovation, you're going to have to test whether that new one does better or worse. And so that's where data science is going to come in to decide not just how to build the algorithms, but how to measure them and how to know if you have a good one. And just to get a sense of sort of how non-obvious all this is and how much variation there is, if we just think about 3 platforms, Uber, TaskRabbit, and eBay, Uber is going to dynamically set prices, take it or leave it, on both sides of the market. So the sellers and the buyers don't pick the prices, the platform does it. They optimize, and then if you push a button, they're going to choose the car for you. And if you think about the urgency and the time sensitivity, they just say, look, no customization is worth the frictions that we might put in there. Then they have ranking algorithms to choose the cars, and that's going to consider things like distance and the quality of the sellers. TaskRabbit was a labor marketplace. It started out with more of an eBay-like model. If you wanted somebody to do something for you, then you would post the task and people would bid for it. That had really high friction. About half the tasks posted did not result in a transaction. So then they redesigned their marketplace so that the workers post hourly rates in general categories, and if you need a task done, you search, and they'll show you people by capability and price and availability. Then at eBay, it started out also as an auction-based platform. Now it's mostly become a buy it now platform. And their ranking rules have shifted pretty dramatically over time as well. And so if you think about all these decisions, like how did TaskRabbit decide? What if you were trying to evaluate or advise, should I change my market design? How would you use data to make that decision? And I had a student who actually wrote her PhD thesis on just that here at Stanford. And so she needed to look at not just basic metrics like conversions and so on, but also she estimated a model of the TaskRabbit worker behavior in order to estimate what would happen if she changed the marketplace design. And so that's the kind of thing that economists do as their bread and butter. Empirical economics is in the business of trying to build models and estimate those models to make counterfactual predictions. It is not widely adopted in industry and in the field of data science, that type of modeling. But for some problems, it can be really essential. I would say probably the biggest success in practice of those types of models is estimating demand. So every consumer packaged goods company has a team of people estimating consumer demand as a function of good characteristics, doing models of imperfect competition, predicting what would happen if you changed prices. So the pricing models are very widely used in practice. But a lot of these platform companies have not done as much with those style of models. I've got a lot of research in that myself. I'm not going to be able to cover it in a lot of detail today, but I'll refer to that back at the end of the talk. So, from an economic perspective, what matters for market design in a marketplace? Well, what theory says is that you should focus on efficiency and long-term participation. Of course, how much you weigh depends on the marketplace. But generally, if you're a platform bringing together buyers and sellers for transactions, you're roughly, the surplus you create, the value created from your marketplace is going to depend on how many transactions you do. So if you have an inefficiency in your marketplace, a friction that keeps people from doing transactions, then you're shrinking your pie. And you can't eat a pie that doesn't exist. So the most important thing is to make a really big pie. And then the second thing is, if you're going to figure out how to charge, you need to figure out how to charge and how to set up your marketplace in order to create frictions in the places where frictions are least problematic. So I'm going to worry a lot about the happiness of the people who are about to leave, and I'm not going to worry so much about the people, if I make their lives a little bit harder, they won't leave. So in the beginning of a marketplace, like Uber needs to bribe drivers to keep cell phones on, and TaskRabbit needs to make it very friendly for the workers. But after they have enough of them on the platform, then the sell side gets squeezed, and they have to put more attention to the buy side of the market or the user side. And that's a measurement exercise to know where you are in that process. You have to understand who is it that if I lower the wage for the Uber drivers, or if I force the TaskRabbit sellers to post their availability and penalize them if they don't keep it current, that's a friction on the worker side. I need to understand, is that actually going to diminish the value creation on my platform? And in some cases, it doesn't diminish it very much because you have enough workers. And so it's better for the platform perspective to squeeze that side in order to make it better for buyers. You get more buyers on the platform. I had a guest speaker in my class from eBay who was VP of selling for a long time. He was really, Todd Lutwick is his name. He's very sharp on marketplace issues. He said he got criticized at some point. He was VP of selling, and people asked, well, how can you be paying so much attention to buying? I'm sure you should change your title to VP of buying. And he said, no. I'm VP of selling. I create value for sellers by attracting buyers. And that's the subtlety of a platform market. You have to understand and measure not just what happens on one side of the market, but how it's going to affect the other side of the market. If you think about how hard it is just to measure one-sided markets, well, those types of measurement of indirect network effects and scale economies from buyers to sellers and sellers to buyers is a very difficult measurement exercise. But it is the most important thing from a theoretical perspective. And then, when we think about the auction design in an auction-based marketplace or the pricing model, what really matters is what happens in the long term. So if I change the way the auctions work, if I change my pricing model, it's easy to measure the short-term effects, and that's what people often pay a lot of attention to. But often, the more important implications are for long-term participation and value creation on the platform. So this is something that back in my old days when I worked on timber, I did a lot of research showing that in timber auction design, changing from, say, first price auction to open ascending auctions, what had a much larger effect when you took into account the participation and whether or not small bidders participated and made the auctions more competitive. So just to think of some short-term, long-term examples in the sort of real world of data science, from eBay, Todd was in charge of eliminating listing fees, throwing away a couple $100 million of fees that they charged to sellers to list items on eBay. Taking away picture fees. They used to charge like 25 cents a picture, another couple $100 million of revenue. So how do you as a data scientist decide, I'm going to throw away $200 million worth of revenue on the theory that I'm going to get it back? Those are the types of problems that I've worked on all the time at Microsoft. And I'll tell you that it's a very challenging problem for a data scientist. It's much easier to say, here's something that's going to make a lot of money in the short run, and maybe in the long run some of that goes away, but here I can demonstrate the short-term benefit. So both of those cases turned out to be highly profitable. Eliminating listing fees got more listings, and in addition, the sellers came to eBay, and when they came to eBay to check on their listings, they also bought. Putting up more pictures made more transactions get consummated. So these are the types of things that you have to think about in terms of market design. So how do you influence market design? Well, first of all, a theoretical framework is key. I've just talked about all these long-term effects and feedbacks across the side of the market and seller elasticities and buyer elasticities. If you don't have a good theoretical framework to build on and just ask your data to speak to you, you'll never possibly find what you're looking for. You'll never make sense. And so the places where theory is particularly important is where measurement falls short. The places where it's hard to measure the long-term effects. So you need to make your arguments coherent, precise, identify these equilibrium and long-term effects, and incorporate the feedback effects and responses. And that's where the social sciences, and particularly economics, can be very helpful. So let's now talk about what you do exactly with data in these circumstances. So data, of course, can inform what kinds of designs will work better or worse in a range of environments. Advocacy for design issues is going to be much more effective if you have a theory and data combined. So if your theory says, here are the things that should matter, and now I'm going to go out and measure this particular elasticity, this seller responsiveness, this buyer responsiveness. How do they respond to frictions? And if I have some idea about the feedback effects, I can try to measure those too. Now, in this environment, we run into a big conflict between, that all sounds good. I mean, how could you run a marketplace without thinking about those things? Well, part of the reason I'm emphasizing this so much is that most marketplaces today, including all the ones that fund our valley, don't do this very well. And they actually ignore these effects systematically all the time. So why is that? Why do people ignore all of these common sense logical things that I just told you? Well, one of the engines of innovation in all of these big tech companies is A/B testing and experimentation. So how do you improve really fast? You have to do thousands of experiments a year. You have an A/B testing platform. You look at the results, and if it looks good, you ship. That's how you can do 10,000 experiments at Google or Facebook and make hundreds or thousands of changes a year. You can't do a lot of analytics on every one if you're going to innovate that fast. But what we see is once we get sort of seduced by this beautiful platform, this experimentation platform, where we have A and we have B, and it's a randomized controlled trial, and revenue was higher in B, so we should go with B. We get so seduced by that certainty, by that clarity, by that beautiful T-stat of 3, that suddenly when you want to start talking about long-term effects and feedback effects and so on, it sounds wishy-washy, it sounds unconvincing, unscientific relative to the beauty of the A/B testing platform. And so that makes it very difficult to then make any kinds of long-term decisions. But that's the way innovation is done, therefore there's a huge emphasis in some directions and not others. So experimentation is crucial, but it has a lot of limitations. One approach is to try to improve the experimentation, and that's a direction that I've been working on. I'm going to spend a bunch of time telling you about that. And then another part, which again I won't have much time to expand on today, but I just advertise, is that if you use more sophisticated models and more sophisticated analytics, you can potentially make long-term predictions about what happens if you change your auction design or you change the marketplace design. But I'll just caution that in practice, even in academics, we spend a lot of time fighting about whether our models are good enough, what are the assumptions. It's a whole PhD thesis to do one of these things. And so in industry, it's often very hard for those things to be influential, even if they're crucial. And again, you really mainly see them being super influential in terms of pricing models. So A/B testing, so everybody knows about this. So we're going to take users, we're going to put some in a treatment group, some in a control group. Beautiful randomized controlled trial. We can get results and know whether we should ship a new algorithm. So when I think about like a canonical case here, it might be a ranking algorithm. So eBay might be putting more emphasis on shipping time. Bing ads might be deciding to match more broadly. If you type in what shoes should I wear tonight, how many ads are a good match for that query? And they're deciding how many to let into the auction. Those are the types of things, that would be a treatment, is one of those algorithms. So standard industry practice for doing any type of algorithm change is to run an A/B test on users or page views to test. So we have a new ranking algorithm. If you come into the website, I'm going to allocate you to either treatment or control. You're going to see either one page or the other, and I'm going to measure how much you click. Okay? And then I'm going to make a ship decision based on revenue and user impact. And again, this is what Facebook and Google and Bing and all of the companies do. But if you're thinking about doing something that's going to affect advertisers, This is actually, I mean, in some sense it's so obvious as to be stupid, and I wouldn't point it out except for that this is what everybody does for, hundreds of billions of dollars worth of commerce. So it becomes, maybe it's not quite that obvious. So there's a number of huge errors here. First of all, the unit of experimentation is not the relevant unit of analysis for thinking about the sell side of the market. So if I'm a seller or an advertiser and 1% of users see the new treatment, that's only a 1% change to an advertiser. It's just background noise. So the advertiser or seller doesn't know they were in an experiment. They don't react. So it's essentially only experimenting on the users, not on the sellers, and so you don't learn anything about their behavior. So that's going to ignore, say, for advertisers, even if their bids and budgets were fixed, suppose that we actually roll out this change and suppose it raises prices for everybody. Well, one thing that could happen is my competitor could run out of budget, and then I get shown more, and then I run out of budget, and then at the end of the day, there's no ads to show, and revenue plummets. That didn't show up in your experiment, but it's going to show up in practice. So this is not like some small effect. It's a huge effect. Also, it affects strategic interaction among sellers and advertisers, and it certainly ignores long-term participation. So what do you do in the face of all of these problems, given that it's super cheap to run user-level experiments, but quite hard to do anything else? Well, there's some cheap, easy fixes, and this is really kind of just practical advice. First of all, you can just try to change what you're measuring. So if I did an experiment, let's use an example from search, where when somebody puts in, what shoes should I wear tonight, I show them an auto insurance ad. Okay. Now, you wouldn't do this on purpose, but we all know algorithms make mistakes, and so suppose your algorithm just happened to make a few more of those mistakes. What does that look like in the A/B test? Revenue through the roof. I'm putting up $30 per click ads on a query that should be worth, 5 cents a click. So I'm going to make a lot more money. That's going to look good in my experiment. And since it's easy to make these mistakes by accident, you're going to tend to ship algorithms that make a lot of those mistakes. And over time, after a couple of months, suddenly you're showing terrible ads, and you didn't really realize it. So one thing you can do is you can actually not evaluate the experiment on the revenue you actually got in the experiment. You can say, some of that revenue I'm going to throw away from an evaluation perspective. So one of the things we did at Bing Ads is we said, well, if they click on the ad and then they click back, so it's a very short click, I'm going to say this was a dissatisfied click, and probably over the long term, the advertiser isn't going to pay for that. Right now, they're paying $30 a click for auto insurance, but if I mix in 10% of shoe queries, they're going to pay only $25 a click. So I'm not going to get that money in the long term. So you actually measure only satisfied clicks. It's not the revenue you got in the experiment, but that's because you don't believe the experiment represents what happens in the future. Another thing you can do is you can do expensive long-term analytic studies to try to relate the short-term metrics to the long-term. Those can be hard, and one of the challenges is that if I measured the effect of one kind of price increase, I don't know that that's going to be representative of what would happen with another type of price increase. So it's partially helpful, but not completely helpful. Another thing you can do is just say, oh gosh, I recognize that my experimentation platform isn't designed for advertisers, so we're just never going to ship anything that hurts advertisers. Or I understand that I'm never going to ship anything at eBay that hurts sellers. But that's pretty limiting, and of course, people are quite heterogeneous, so you might be really limiting your innovation trajectory into particular directions. So these are the kinds of fixes that people do in practice when they actually get a little bit sophisticated, but they're not perfect solutions. So a slightly more expensive solution is to do a long-term advertiser or seller-based A/B test. So it needs to be long-term because sellers on eBay or advertisers on Bing or Google or Facebook are kind of slow to respond. Some of them are optimizing all the time, but some of them only check in every month or so, or some of them only reallocate their budgets every 3 months. So you have to give this some time. So what I could do then is I could say I'm going to take some sellers and I'm going to give them one algorithm, and other sellers and give them another algorithm. Well, first of all, that's actually kind of hard because they're sometimes showing up on the same page. So sometimes that's not even technically possible. Let's imagine we've got an algorithm for which it is possible. Then what would we do? Well, it's expensive. We would have to watch it for a long time, and it's going to ignore advertiser interactions. So then you might come to the point of saying, well, maybe I should measure how important those interactions are to start with so I can figure out which ones to ignore. Maybe I can find some isolated advertisers that are far enough apart from each other that they're not going to interfere with each other. So just to sort of think about this interaction, here's some examples. So we just had Halloween. Imagine you go to eBay and you start shopping for costumes. You might shop for a How to Train Your Dragon costume. You might, and by the way, I'm not going to say this is for my boy because this was what my girl wore. If you had a girly girl, you might search for a Frozen outfit or perhaps for your son. But you might also, while you were there, shop for How to Train Your Dragon toys. So you can imagine there might be some How to Train Your Dragon focused sellers, and there might be some costume focused sellers, and they're going to interact. So I can think in general of e-commerce markets like eBay, Amazon Marketplace, and Bing Ads, Google Ads as bipartite graphs. So everybody is in some way linked to everybody else through the overlapping queries they're shown with. If you think on eBay, how do people compete? It's in these lists of products that are shown. And so how competitive a seller is depends on who eBay puts up next to each other. So I can think about the sellers being linked to queries and therefore linked to each other. Now, what I might ask in this kind of network is, can I test whether there are peer effects or whether there are friends of friends effects? And of course, this is something you might also ask in Facebook. And in the research paper I did this, I worked on this. We worked with people from Facebook. So how can I test these hypotheses? Well, actually, amazingly enough, there's sort of an unsolved statistical problem of just how do you test hypotheses on networks? Because, of course, everybody is sort of correlated with each other, and how do I do my asymptotics? If I have all the sellers on eBay, what does it mean to kind of grow the sellers? Like, I have them all. Okay, well, Jennifer's smiling. So, of course, Jennifer did some work on how to do this. But, you know, if I think about I have all the MIT undergrads and I've given them all Bitcoins, that's another experiment I did, network experiment. I don't really want to grow the MIT network. I want to look at the network I have. So what I did with a couple of co-authors is we developed a theory for how to do exact hypothesis tests without making any assumptions for various hypotheses of the form treating unit J related to unit I in way Z has no effect. For example, friends of friends have no effect on me. Or only the fraction of my neighbors treated matters, but not their location in the network. So what we did was we extended Fisher exact hypothesis testing, or permutation tests as they're sometimes called, to these non-sharp null hypotheses to come up with good ways to test interactions. And so in principle, in my advertiser or seller example, I could test the hypothesis that, say, two links of a certain distance aren't important, and then I could ignore them, and then that would help me design experiments in this network setting, only focusing on interactions that were tested to be important. So another way that you can think about this, suppose interactions are important, like these sellers compete. They change prices in response to each other. So I can't reject that they don't matter, and I really need to think about their interactions. So a second class of solutions is to do something called community detection and try to divide my network into some subnetworks that hopefully don't interact too much. And then what I might do is experiment on the network, on the subnetworks, and say, well, that's going to tell me what would happen if me and all my neighbors were treated, or if me and all my neighbors were not treated. So this is a current area of research. For example, Johan Ugander, who's a professor here at Stanford, was a postdoc at MSR last year, has done some work on this with Kleinberg and other co-authors. And so what they try to do is they try to say the treatment is having a high share of friends treated. And the problem you're going to have is that you're going to have people, since these aren't really non-overlapping networks, people on the boundary of a subgroup are going to have a lot of friends who are treated, but also friends who are not treated. So they're going to see a mix. And of course, it's not random, the people who are on the edges of groups, rather in the center of groups. And so even though you did a randomized experiment, the people who actually got fully treated is not random, because it depends on their place in the network structure. So Ugander proposes this propensity score weighting to adjust for the non-random assignment to being fully treated and ignoring some of the people. Like if you have too much overlap, you get cut out, and then I try to adjust for that selection. This is really an open area. It's something that folks at Facebook and other places are actively working on. And it's a very exciting area, I think, really interesting. Okay, so then putting that together, a long-term solution based on this would be to cluster advertisers, do a bipartite graph that helps you figure out good clusters and experiment on the clusters, but then you have a hard analysis problem afterwards. So two more approaches that I've worked on are approaches where you try to study heterogeneous effects and make predictions from that and build insight. or do economic models that require a lot more assumptions, but then make much more specific predictions. So again, I won't tell you the details today of the economic side because probably it's pretty far from the way most people here do their work. So let me spend the rest of my time talking about A/B tests and heterogeneity. So I'll use a motivating example as an experiment I ran on Bing where we flipped the order of results. So we took position 1 into position 3, into position 5, or into position 10, and saw how many clicks you lost. But an experiment like this is going to have quite heterogeneous effects because for some types of queries, position would matter a lot, and for other types of queries, you kind of know where you're going, and the rankings is going to have less of an impact. So, this isn't the kind of experiment that you run every day. This is the kind of experiment you do to derive insight, but I'm going to use it for analysis because it's a clean one that's easy to describe. Okay, so I want to learn about heterogeneous treatment effects in this setting. So if I can see that some types of advertisers are really affected by a treatment and others are not, that can help me make long-term predictions, especially if I know that some advertisers are also not very responsive, for example. So if I hurt really responsive advertisers, that might be a very different type of concern than if I hurt advertisers who never pay any attention anyways. So what I do in a series of papers is figure out how to systematically measure heterogeneous treatment effects. I'll talk about it today in A/B testing. We also have it for observational studies as well, but all the math I'll show you today results are from A/B testing. And so this is something that actually we're having a lot of interest from tech companies in building into their A/B testing platforms. And so the idea is that when you run an experiment, you'd like the engineers just be able to push a button and say, well, how did my algorithm work? Where did it work well? Where did it not work well? That gives them insight that they can use to make better algorithms. It also would allow you to say, well, we got a statistically significant positive effect in this particular vertical or for these particular types of queries. So we can go ahead and ship your algorithm there, but you need to go back to the drawing board on other parts of the platform. So it can be used for decisions. So there's actually, I have two papers, one with Hito Imbens, one with Stefan Wager, who's a stats department PhD student, where we do two different things that are complementary. So one paper tries to do data-driven searches for subgroups. The other does fully personalized predictions. And I don't think of these as competitors. I think that they're complements, and they're really also for somewhat different purposes. So if I'm trying to gain insight, it's nice to see, okay, here are a few subgroups. If I'm going to make a ship decision based on a t-statistic, which is what a lot of the A/B testing platforms do, I better have good confidence intervals, and I want to understand, which group of queries could I ship this algorithm for. If I wanted to put a flowchart up in a doctor's office, it needs to be a fairly simple set of subgroups that people use. On the other hand, if I'm going to, give personalized advertising on the fly, if I'm going to give personalized web page design on the fly, I just want the best prediction for every individual. So in one paper we use cart-based trees, and the other paper we do random forests. So the segments are good for interpretability, but they're not the best predictor for any individual. There's also a problem with segments being unstable. For personalized predictions, we've developed now the first asymptotic normality results for this, so it can actually give you confidence intervals, but no method is going to give you great confidence intervals if you have 1,000 covariates and 10,000 observations. I mean, it's just not possible. So in those methods, you're going to be limited by sample size, especially in big data applications. So essentially, I guess I'm running a little bit out of time, but if we do the regression trees, let me just show you what our proposal looks like. What we do in what we call causal trees is instead of building a standard prediction tree, we go after causal inference. We modify the methods to actually have causal inference as their goal, and that changes every aspect of the algorithm. It means that I'm going to be focusing on estimating treatment effects rather than predicting outcomes. My splitting criteria need to be focused in that direction. And one of the things that's really kind of novel about estimating causal effects is that you don't observe the ground truth for any observation. So I could give half of you a coffee and half of you not a coffee, but I don't observe for any individual in this room the treatment effect of coffee. So if I did a 10% holdout sample, if I tried to estimate my causal effects and then see if I did a good job, I don't actually have a ground truth to compare it to. So we'd propose a couple of ways around that, either estimating the out-of-sample criteria or using statistical theory to complement the observables. So but it's actually a fundamentally different problem. But the key point is that if you're trying to estimate causal effects, it is super important that you get the causal effect. You don't care about the mean squared error of predicting outcomes. If you regress quantity sold on price, you often get the wrong slope. That is, the higher the price, the more the quantity sold in observational data. Economists are very used to a setting where we don't want to fit the data perfectly, but rather we need to only use variation in the data that will actually give you the right answer, reducing predictive mean squared error, but getting a more accurate causal effect. And that's what we're going for here. And then in terms of, so we apply it to search. I'll just show you a picture of the personalized predictions. We have a random forest version of this, where we actually average up the causal trees that we estimate. And we're able to show that we do a lot better than k-nearest neighbors in terms of both bias and variance. And the big problem is if you have lots of covariates and you try to do nonparametric estimation, you just have way too many neighbors, and they're all very different from the person you're predicting for. And something like a random forest or a machine learning algorithm that's adaptive is going to find which neighbors are important. And the real innovation we have is trying to do that in a way that's unbiased and that gives you valid confidence intervals. And so that's what we've done, and it allows you then to use it for inference and for statistical decision making. So just to sum up, the conclusions here are that doing data science for businesses, particularly economic marketplaces, which are the heart of a lot of the new economy, is super interesting. It's super hard. Your off-the-shelf experimentation techniques, your off-the-shelf prediction techniques do not do the job. You have to really modify the techniques for the economic scenarios that you're in, and that's exciting because that means that if you can figure it out, you have unique value to bring, and you can really make a big impact both on the scientific inquiry and on the real-world problems. And so I think it's just a really great area of research and for industry, and so I hope that some of you get inspired by that and be the next generation of market design data scientists.
Thank you so much, Susan. Fabulous talk.